welcome to this presentation about Susan's ride on Campus 2030, a project on sustainable smart road infrastructures. My name is Dan. I'm professor of teletraffic systems at the School of Electrical Engineering and Computer Science, the Division of Network and Systems Engineering. Susan's ride on Campus 2030 is a truly interdisciplinary project containing researchers from the School of ITM, the School of ABE, and the School of ECS. The motivation for Susan's ride on campus is that non-optimized road construction, as we do it today, leads to rotting, cracks, and potholes, and these in turn harm traffic safety and lead to increased maintenance needs of the road infrastructure. Now, road maintenance today is mostly reactive, and it's actually fairly expensive, between $1,000 and $20,000 per kilometer per year, according to estimates. What we posit is that data could be collected during construction and could be used during construction and the operation of the road infrastructure in order to decrease road maintenance costs. Our objective in the project is to demonstrate the potential of digitalization in the area of road construction, operation, and maintenance. We would like to show the potential of data-driven construction, operation, and maintenance, and we want to point out, identify the lacking systemic structures. Our approach in Susan's ride on campus focuses on data, models, and the infrastructure. We consider three phases of the life cycle of road infrastructures, starting with construction, where what we can do is to improve decision support, provide improved decision support in real time for those who are involved in the construction of the infrastructure. The second area is predictive maintenance, which allows us to reduce the costs of reparations. And the third area is to adapt traffic behavior to the instantaneous road conditions. We use models, data, and algorithms for achieving these objectives, and we are working on a number of use case demonstrations. First, on real-time feedback to the operator during road construction about the compaction process based on online predictions. The second demo is predictive maintenance of the road infrastructure based on life cycle data that were collected during construction time. And the third one is the adaptation of the behavior of autonomous vehicles based on the state of the road that is obtained in real time. Let me start with the case of smart compaction. Now, compaction today focuses on producing a smooth road surface. In the case of smart compaction, we could add as an objective to learn the parameters of the material used for compaction while producing a smooth surface. Why do we want to have the material parameters? Because they are useful for improving the compaction itself, avoiding damage, for example, and they can be used for predictive maintenance. Now, how can we make this actually work? Imagine a roadbed, a section of a road. Say we divide this roadbed into n slices, and we assume that the slices are homogeneous. For such homogeneous slices, there are finite element method models that can be used for estimating the permanent deformation of the road in response to the force that the compactor puts on the roadbed. One example is the viscoelastic Berger model. This model basically predicts, as a function of time, so how long do we put pressure on the road surface, what will be the deformation of the road surface over time. We see here there is an elastic part and there is a permanent deformation that remains even after compaction is over. This model, for example, has 4 parameters that are used to describe the behavior of the material. Now, how can we use this? How can we learn these parameters through repeated interaction with these slices of the roadbed? What we propose in the project is to formulate this as a parameter estimation problem. Initially, we have a prior of the parameters. Over the course of time, we can execute actions which will be the loading through the compactor and the amount of time during which this loading is applied to the slice of road. We make observations of the deformations, and our objective is to minimize our uncertainty about the parameters of the material, subject to the constraint that we want to have a smooth road surface. We propose the methodology for solving this problem. Basically, what we do is we apply a surrogate neural network approximator of the finite element method in order to accelerate computations. And we use approximate Bayesian computation for updating prior. How does this work? We start with our initial prior. We choose the prior for choosing the loading and the amount of time to be used in a way that minimizes the BMSE. We then observe the actual deformation, and we use the actual deformation for computing the posterior of the parameters using approximate Bayesian computation. And this is where we use this surrogate neural network. We then use this posterior as the new prior, and then the loop continues. If you would like to read about more details, I refer to the paper that appeared recently in the European Journal of Control. The second area that I would like to highlight is infrastructure-aware autonomous vehicle operation. In this area, we have developed an information architecture that can combine different information sources for adjusting the behavior of an autonomous vehicle in real time. So in this example, we show information obtained from the Swedish road authorities' information infrastructure about road conditions, for example, potholes. And we see real-time information about weather, other participants on the road, and so on. All these information are entered in a database that basically serves as a digital twin of the environment. And this information is then used for influencing the local planning of the vehicle in order to avoid obstacles that are known to be on the road. To show you an example, you see here an autonomous vehicle driving through an intersection where there will be a pothole around this location. And what you see is that the path planning module takes this information into account and basically modifies the optimal path to follow for the autonomous vehicle. After the pothole is passed, the vehicle returns to the original optimal path. In the future, we plan to continue our work on smart compaction. We want to develop a simulation-based demonstrator of smart compaction, and we want to calibrate this using real-world compaction data, and then finally visualize this. We also continue the work on infrastructure-aware AV path planning, collecting data using the 5G infrastructure, visualization of how the path planning is affected by real-time information, and implementing this in real life on the KTH campus. In summary, Susan's ride on campus paves the way to sustainability. Overall, improved construction can reduce the carbon footprint in the construction industry. 95% cost savings could be achieved if cracks are detected early. And it also leads to improved traffic efficiency. With this, I thank you for your attention. And if you would like to read more about the project, please visit our website on the Digital Futures web pages.